Great. So we're going on to just a series of 3 10-minute talks, one after another. And the first one, pleased to welcome Nooshin Javaheripour from Germany, the immediate and delayed effect of ketamine and brain functional dynamics. Thank you very much. And sorry about the pronunciation of your name.
It's not working? Okay. I would like to thank the organizers for giving me this opportunity to present our work. I have no conflict of interest. Our group proposed the biphasic mode of action of ketamine theory in 2014. It tries to explain how an acute infusion of ketamine, which is only available in blood for the time of infusion, can induce an antidepressant effect after 24 hours. This theory has... This theory has two critical phases. In the acute phase, the person may experience transient dissociative effect, and within 2 hours, the antidepressant effect appears and peaks in 24 hours. The main clinical aim for the treatment responders is sustaining the antidepressant effect. This theory has multiple dimensions, and the focus of my study is on brain dynamics. It states that ketamine can disrupt the brain network temporal organization during the acute phase, and this temporal reorganization of the brain allows for the classic reinforcement. And reinforcement only works if we can create contingency. In other words, connectivity can be reinforced through the fluctuation of brain dynamics. Hence, and ketamine may enable the brain to adapt to an alternative rearrangement that leads to reconfiguring the connectivity patterns in the delayed phase. So it is the combination of plasticity and ketamine changes that allows us to change the brain patterns in delayed phase when the antidepressant peaks.
No, it should be okay.
Thank you. So, based on this theory, we have the following hypothesis. Changes in dynamic patterns are associated with static functional connectivity patterns. Dynamic changes are restricted to the acute phase of action, late functional connectivity changes are expected within default mode network. And acute dynamic changes can predict delayed functional connectivity changes in default mode network. So to model the brain dynamics, we used hidden Markov model. We can see here that the signal from different brain parcels fluctuate across time. This approach to brain dynamic models tries to find a part of the both signals that have similar pattern of activity and connectivity across the parcellation, as can be seen in these colored blocks. And where each blocks is called states. These blocks do not occur sequentially, and the model provides the probability of moving from one state to another state. This method provides additional individual temporal features such as fractional occupancy, the time spent in each state, and lifetime, which is the average duration of a state per visit, indicating its stability. So Modeling the whole brain dynamics, we found 8 states. This heat map shows the mean activity of each state, each parcel in each state. Ketamine acutely changed the temporal features in 2 states by decreasing the fractional occupancy and lifetime of one state and the increased temporal features in another state. And the fractional occupancy of state 7 was associated with increased in disembodiment score. The functional connectivity between networks only occurred only increased during the infusion in the acute phase, and the acute static functional connectivity was correlated with the temporal features of the significant prominent changes in dynamics. However, we didn't detect any whole brain temporal changes in delayed phase. So the dynamic in the default mode network was more diverse, and we found 9 states with significant decrease in two states. And the connectivity, but unlike the brain-wide connectivity, we found both acute and delayed connectivity changes, and but we didn't find any prominent dynamic changes after 24 hours in the delayed phase. And the late connectivity changes were associated with reduced lifetime of the state 9 in the acute phase. So in summary, acute brain-wide dynamic changes during ketamine exist, and their correlation with acute connectivity changes support their underlying dynamic nature. And as I said, no dynamic changes were detected in the delayed phase, and only for DMN we do see late FC changes that are predicted by acute dynamic changes. Our results support the biphasic mode of action of ketamine theory, as the temporal reappearance of the states allows for classic reinforcement, and reinforcement relies on the ability to create contingency. We can only strengthen the connection if this state reappears spontaneously, and the combination of plasticity and dynamic changes allows us to change the brain, and adding the complementary therapies such as psychotherapy is needed to shape and maintain these changes. Thank you.
Any questions? Oh, yep, question over there.
I was wondering if you could talk us through your state selection process. So how did you end up choosing that number of states, and do the results vary much when you varied across state numbers?
So we need, for the hidden Markov model, we need to choose finite number of states. First, we run the model for the quite from 4 states to like 40 of the states, and based on the free energy changes, and we choose the number of states which fits the minimum free energy.
Okay, thanks.
Maybe I can ask one very quick question then. So it sounds like you have quite an elaborate model of how ketamine works, and that your results very clearly show that ketamine causes these changes in the brain state. And we know that ketamine improves symptoms of depression. I guess the missing piece is that these changes in brain state mediate that therapeutic effect of ketamine, right? That seems to be outstanding, that question. I wonder if you have any plans to to demonstrate that it's the people that have these changes in brain state, the patients that get better with ketamine.
Yeah, that's the other.
It's working.
Oh, it's working. That's the other plan. Our group is collecting patients with MDD, and we are going to have a baseline to check the states and if these states are reduced or increased during infusion and how it works after infusion.
I see.
Yeah.
Thank you very much.
Thank you.
Thank you again.